I guess it's at 4 o'clock on Monday that Nick Rosenblum is talking. We're in the big room at Bay. So he does all kinds of things, and I hope he's a good lecturer, and I hope it's very interesting. I don't know what we'll do if everybody in the room upstairs is over to Bay and is over. Well, inquiries, and I said I announced it to a large group of people, and a number of them might go, and they said, "Oh, they're not going to go." So I don't know. They were going to. I don't know if it's being recorded. Oh, it is being recorded by the department. So, all right. So I just wanted to say one other thing on the Riemann hypothesis. So this is the reason why we like the Riemann hypothesis. If phi of x, which would be for any positive number, but particularly large, say x bigger than 1, if p of x is the number of primes, then you have something that would be undreamed of, perhaps, by the 19th century mathematicians that studied the prime number theorem, which gives a very weak estimate. This is very well approximated by the integral logarithm. And to be more precise, it's less than or equal to some constant, which I think is explicit, that depends on epsilon. For any epsilon greater than 0, it's less than c epsilon x 1/2 plus epsilon. Now that's very good. If you had log x over x, excuse me, x over log x, it would be terrible. You wouldn't get any power of x. You'd be x to the 1, and then maybe there'd be some epsilon power to the logarithm, or divided by some epsilon power to the logarithm. Very bad. So this is for an explicit constant. So I mentioned this because this is, I guess, why Riemann zeta function is interesting. I guess there's other reasons too, but this is the big one. So for an explicit constant c epsilon, if the Riemann hypothesis holds. So as I think I mentioned verbally last time, it work out something like this. This is no good for x not very large, but in fact that you're interested in prime numbers and they go on forever. So the question of how many prime numbers there are involves all possible bounds that you would large bounds you would take on the primes. And so for example, if x equals n to the 100, turns out that Li of x is more or less like n97 plus or minus some stuff. And so that means that there's easy to calculate. Well, I've never done that, but it's quite elementary to calculate these bounds on Li of x. So that would represent the number of primes. This represents x. That would represent the number of primes less than or equal to x. And the error term, well, that's x to the 1/2 plus epsilon. So that's more or less 10 to the 50th. That'll be a very large number, but take all primes less than or equal to 100, you can write down exactly how many there are, up to 47 places. So that's very okay. And this is why numbers here are slow. Okay, so this is a course about this program. I always say, well, the Langlands program. The answer is well, there's no direct path, even a very complicated path that would people that know that might lead to the Riemann hypothesis. Unlike some of the other big conjectures in the Langlands program, there's we'll be talking about them soon. The big conjectures in some of the big conjectures in the Langlands program, there is a path. It's very, very difficult, and not all mathematicians think that it's the right way to go or is going to be doable. But at least it's a well-defined path, very deep and complex. That is not the case, as far as I know, for the Riemann hypothesis. But there are some very provocative observations that one can make as far as the Riemann hypothesis is concerned and the Langlands program. And so we'll get to those maybe next week. Okay, so this is all to introduce actually Hey there. What the Langlands thing, part of the Langlands program, it's one way to view the Langlands program. There's 3 different ways to view it, and to view the data studies. Different ways to view the same data, but one of them is through functions like the Riemann data function, specifically Dirichlet series. All right, so a Dirichlet series is like the Riemann zeta function, with some n going from 1 to infinity, of n to the minus s. But a general Dirichlet series, you allow yourself to put in coefficients. I'll follow an sigma n going from 1 to infinity, n to the minus s. So the an's are complex numbers. Ns is a complex number. And you want to check easily that this series converges absolutely. So I should say series converges absolutely for the real part of f greater than k plus 1, any integer k, if an, these coefficients, you do need some kind of bound. It can be weaker what you have for the Riemann data function. But if an is less than or equal to p times k, say for k, Dirichlet series would converge absolutely to the real part of s bigger than k plus 1. So those are natural things. They're natural ways to display these coefficients, and indeed, you can sort of imagine that they might be interesting if the coefficients themselves arrive in a different context. Then this is an interesting way to kind of display them in the form of an analytic function for the real part of k bigger than n. Special. I don't think actually there's an agreed upon definition of what an L function is, but I think maybe that usual one, an L function. So the Langlands program concerns L functions, and an L function is a particular kind of Dirichlet series. And so by definition, we want to take this as definite. It's any Dirichlet series that has an Euler product. Like we saw for the Riemann zeta. So what we mean by that is, if I were to write L of S for any the Dirichlet series, if I were to write L of X, so any Dirichlet series L of S any Dirichlet series L of S that has an Euler product. So in other words, i.e. L of S thing we assume has divergence in some right half plane can be written as a product over all primes. Of a sum of the product over all primes, like we did for the Riemann zeta functions. In that case, we have that for each prime, we actually have an infinite product, e to the minus powers of minus s got from the geometric series. This would be more complicated, but it would just be some k going from 1 to infinity. Not for the geometric series, you have 1 there, and then e to the minus ks. That would get a e to the k. That be more general coefficients. E and e minus ks. An infinite product of these things, where you take only the values of the coefficients at prime powers, and then you have a sum of them and a product of the sums. And that is exactly the same thing as would happen for the Riemann zeta function. You can express this sums over different elements taken from the different products, giving you products of the powers of a prime number, and to get a sum n. And so this, if it has an Euler product, so this an Euler product doesn't always exist for an arbitrary Dirichlet series. The condition is very natural. It is so we'll have an Euler product if and only if the product of 2 of the coefficient of the product, whenever, not always, but whenever, and they are relatively prime. And so just a rather strong condition that leads to an Euler product. It's customary when it does have an Euler product to write this, so this notation, write it as the product over all primes of the local L function, being the LP of that state. This the simpler thing where you just have coefficients attached to the power of the given prime. Okay, so that's a L function, and so this is what the Langlands program studies or needs to. And so let's say automorphic L function. So automorphic L function are certain coefficients. Excuse me, certain L functions whose coefficients interesting arithmetic information. Right, very naturally, they were introduced in a paper of Langlands in the Wagner in 1969, 1970, in the Wagner symposium, that 49-page paper to find for these. You can use the word automorphic. It wasn't that vogue at the time, but he defined sound function. All right. So there's two aspects to the Langlands program that I could just say right now. One is to identify the kinds of data that would go into this definition. And the interesting arithmetic, just the third, very interesting arithmetic data put into an algorithm. Thing that's did that. There's something that's a lot deeper than that, and it is this is the part of the program that this our interesting arithmetic data, these guys have a completely different way of being able to arise in a completely different way. They arise from analysis, and they arise from eigenvalues of differential operators. Well, actually, that's not quite correct. There are differential operators, and I'm just saying stuff. We'll do it. Don't worry about it if you're not familiar with it right now, but there are certain differential operators that arise from geometry. They're known as Laplace-Beltrami operators on certain special kinds of Riemannian manifolds and Riemannian symmetric spaces. And so those are part of these things. Those things, the eigenvalues of those things go into what would be, if you remember, when we were talking about the Riemann zeta function, we wrote lambda, we expanded over pi to the minus s over 2 times the gamma function. I'm not committed to memory, but you remember what it was? So gamma that's over 2, gamma that's over 2. Zeta. This is what you had to put in to get a nice function. I mean, you still get a functional equation without this, but it would just be more complicated. So let's put that in, you get a very nice equation, functional equation. So the thing is that the eigenvalues of the Laplace-Beltrami operator are what give you this data. When you have an automorphic L function. What gives you this data? Let's start with arithmetic information. It's so I think in quantum mechanics, of which I'm no expert, but I think that they call things the Laplace-Beltrami operator is like a Hamiltonian quantum mechanics. I think they call it Hamiltonian quantum mechanics. And then they are also interested in observables, and use the term observables that are related to that, and specifically what they are operators that commute with the Hamiltonian, or Laplace-Beltrami operator in this case. And those are the things in the Langlands program give you this. So they're observables. I think that's the correct term in quantum mechanics. Operators that commute with the differential operator, the underlying differential operator, Hamiltonian. One's talking about physics. I mean, the physics have different. They arise. Quantum mechanics arises for different manifolds, not all specifically at the beginning of the ones that have the Langlands program. But in any case, you have this Laplace-Beltrami operator on a certain very specific kind of Riemannian manifold. Then these things come from operators, manifold, or the function of the manifold that commute with the Laplace Beltrami operator, and they're called Pekka operators. These are eigenvalues. Think more about this later. Eigenvalued Pekka operators. Natural operators on the kind of manifolds Langlands program aims to turn around your triangles. And this comes about, not this specific one, the Markovian one there. I'm oversimplifying this, but class Beltrami, an actual differential operator. These are sort of roughly speaking, they're sort of like difference equation operators. Langlands actually put all of it together in that article definition. It's a little hard to read because these are quite ordinary things that we this would have been hard for anybody to write it up in a really clear way, but they're all there. Yeah. What he used the notation, he defined this system. This is the notation now that's used for all of morphing theory. He didn't write it as just something like this. He wrote it as L infinity of S, with the understanding that it's like the local L function that you attach to D, but it's attached not to B, but to the Archimedean prime L infinity. And then he defined the L function, which is all in the place. So Langlands notation. And also, he didn't write L of S to be product over all times. He wrote L of S for the product L infinity from the product over all primes. Yes. Anyway, that's not a big deal. And then the functional equation was a very simple thing. The proposed functional equation that related L of S to L of 1 minus 6. So that was set up. He actually presented his conjectures in terms of L functions. There's other ways in which you can introduce them, but that's the way he did it. He actually proposed in that article 7, I think I mentioned 4. He didn't call them conjectures. He was a little weary of calling them conjecture. And really, yes, he's pretty sure, but he didn't want to state things as conjectures. Wasn't completely sure, so he called them questions. So he has 7 questions. And the first one, because of the definition of these L functions and all of the properties, things, conjecture properties, and later questions, the conjecture properties of the things that go into these L functions. The data, A, P, K, and the data that would go into the eigenfunctions for operating. Question, yes.
Just a clarification.
Yes.
So you're saying that the L function is a product of the L infinity part, which is related to the Laplace Beltrami,
Yes,
and a product of these LPs,
yes,
each of which is associated to a Hecke operator.
that's correct.
The Hecke operators are parametrized by the primes,
Yes,
but they're all acting on the same symmetric space.
they're all acting on the same symmetric space, and they all commute with the Laplace Beltrami operator. I mean, people put the Hecke operators together. It's more complicated. I mean, there's say Hecke operators can be defined early in, but they they put together, these are the basic ones. And then you get to get them all, or it's a little, the formula is a little more complicated if you put the Hecke operators together for different peaks. What you say is correct, that's the essence of it.
But roughly speaking, there's a correspondence between L functions and symmetric spaces, some way. For each L function, there's a specific symmetric space.
Yes.
Yeah, roughly speaking.
It's not just any symmetric space, it's a symmetric space. I guess a negative curvature. It's the quotient of a fundamental group also has to be an arithmetic. Or specifically, precisely what's known as a congruence. It's like for the upper half plane, it's the set of integral. We like the set of integral matrices that are congruent to one number 8. And then it's just a little bit more complicated than that. What I have defined here would be called the unramified L functions. The ones that would arise if you were dealing with the fundamental group SL2Z. If you were dealing with symmetric space, the upper plane. So that the global symmetric space of the upper plane. If you were dealing with things that are congruent to one mod n, that's a smaller fundamental group. And for those are the divisors of n are what are called ramified. And they have a different contribution to the L function. That's very interesting and so right? But doesn't matter though. This is the essence of what I mean. I'm going to be talking about these things in detail. Anything else?
Morally, should the functional equation and analytic continuation be baked into the definition of L functions, or are there other arithmetically interesting examples that don't have this?
There's can you just repeat that?
So morally, should the analytic continuation and functional equation also be in the definition of L functions?
Well, I that's a good question. I think that there's some I think people are all over the map on what you're going to call an L function. But you're quite right. And this is the broadest definition. Something that satisfies another product. I think you're right. Some people call it an L function. They want analytic continuation and functional equation. All right.
Sorry, did you say these symmetric spaces are all quotients of the per half plane?
No. That's the simplest one.
I see.
That's a symmetric space. Well, we'll get to it, but a symmetric space is a semi-simple Lie group modulo a maximal compact subgroup. That's a symmetric space. That's what's called a globally symmetric space. A very special case being the upper half plane, which itself is SL2R modulo SO2.
Right. So sorry, I mean the ones arising in this way via this correspondent to L functions. Those are also more general than just quotients of the upper half plane.
Yes. The upper half plane had been studied. I think some of the theory was introduced by Dirichlet, well, I guess Dirichlet, but I mean not so much at the very beginning, but Poincaré set of modular forms. So that was around, but this is what was the point of Langlands' paper was to introduce a huge raft of these things that came in much more general contexts and which conjecturally gave very general answers to questions people have been asking about number theories. All right, so okay, so interesting arithmetic information. So let me say a little bit more about what the form that takes. So this is a totally different direction, but this is the stuff that's one does in algebraic number theory. Of course, it's an algebraic number theory for a long time. arithmetic information. Okay, so there's two kinds of number theory. There's algebraic number theory, and that's you're interested in fields, number fields, extensions, solutions of equations, of polynomial equations in one integral polynomial equations in one variable. That's algebraic number theory. Analytic number theory, as I guess you're interested in bounds, product formulas, simplifying very greatly, but the sort of things that the Riemann hypothesis would answer. So algebraic information would be supposed to have that f of t is a polynomial equation, variable with integral coefficients, and let's say leading coefficient 1. Okay, so this is a harmonic polynomial. I'll call this said that that's what I'm saying. But okay, so you got that. That is such things give you Galois extensions, the rational numbers. So let's write via that. Corresponding field. That over Q. And so that's where you get Galois extensions. So let me write gamma of that. Galois. Okay, so whatever it is, it's a subgroup of Sn symmetric, because you join the roots of the end roots of the equation and take the core field that they generate over to that they generate. So right, I guess people that study these things find that most polynomials, many and perhaps most in a certain sense, give a full symmetric group that Galois group, but the other one particularly interesting. But in any case, if the subgroup is a symmetric group, I guess I have to be a little bit careful. You would have to order the roots to actually get it as a subgroup of the symmetric group. And it's you don't order them if you're not doing it, you're given this equation. Then it's a conjugacy class of subgroups, the symmetric group. But so this is you have to order the roots to actually have this as a subgroup rather than conjugacy. Case. Beginnings of algebraic number theory. So I'm sure many of you are very familiar with what I probably say, but so here's the question. Well, the thing made to order, this equation, integral coefficients, it's made to order for finite fields. So typically with equation of irreducible over natural. Right thing. Must be. That is that interesting? If you do it, you're going to get f of t being equal to f of t. So on f r of t minus e, where f I of t is irreducible. And what is particularly interesting from the point of view of algebraic number theory, not being able to do this for a given time, but how these things vary, what happens to these things, p varies. All right, so it's customary for reasons that one sees right away at the beginning of the course in algebraic number theory. If you factor mod p for a few primes, finitely many primes, you're going to have some repeated factors. You don't like those, or say you don't. It's not that you don't like them, but the simplest question is if you look at the ones that have distinct factors. So posing this question, at least initially, let's discard finite set S primes P such that factors Fi T are not extended. So as you run the car, even sort of basic graduate algebra course, you can write down what conditions each thing you're going to have to satisfy to not have distinct factors. You can form the discriminant of this polynomial. The discriminant of this original polynomial will be, you take this polynomial, you could think of this in the ring, you could think of the coefficient, you can think of this polynomial as the ring as T. This unique factorization thing. And you could take this polynomial and then you could take its derivative. And there's going to be at least the greatest common divisor of this polynomial and its derivative. That would be a polynomial of degree n-1. And that is the discriminant. Got that right? So it's divisors of the discriminant. This polynomial is done by taking the derivative of the original polynomial. It's divisors of that are going to have repeated roots. This as would be might not be easy to calculate, but that's not the issue. Well, P by discriminant. And then so let's throw away then some of the questions posed now. Some of the questions that I would pose end up not being very having reasonable answers for people to include the primes that have repeated factors. So what we would do then is agree that we get a map. Extending any prime P to the set, I'm going to write it as pi sub P, and it's the set degrees of this of the irreducible vectors. We were that thing. So it's a set of degrees of these irreducible factors. Mod P. So it's set N1 and R. And I so this is a we get map from so this is a map domain is primes I'm sorry, this is not incorrect. I want to consider primes that do not divide the discriminant. Okay, so that's a set of these. Not dividing the discriminants. Then map those. I want to map this set of primes to the partition of n given by the degrees of its irreducible factors. This is the primes. Partitions. And that's on the right, maybe table 5, a partition for a partition. And one way to phrase a basic problem, algebraic number theory, really is closely related to possible classification, is what is the image of that map? What can you say? General terms. The image would be all partitions. So I phrased that wrong. I'll say this again next time. But what's particularly relevant is the preimage of any partition. Given partition of n, do this. Partition of n, and given this polynomial, I enter this polynomial mark p for all p. And then what's particularly interesting is the set of primes. They got this whole set, which give rise to this partition. And that's we'll see next time. We'll review next time. That's very very relevant. Here it is. Thank you. Yes.
So this map is surjective, right? Onto the partitions, right? And that set S, should it be the primes dividing it's the discriminant rather than not dividing?
Not what you're doing. Yes, you should. Find this part. Well, that gives you all the really some information. That's how you know into the report. All right, so next Wednesday we're meeting in another one. So okay. I thought.